Hey everyone, welcome back. This is episode 4 of the AI Agent Memory series. Last time, we covered the 4 types of memory and how data moves through the lifecycle: extract, consolidate, retrieve, forget. Today, we go deeper. We meet the actual systems that engineers built to solve the memory problem, starting with the one that sparked it all, MemGPT. Before we dive in, picture a brilliant AI assistant. Gives you perfect answers, but every morning it wakes up with zero memory of yesterday. Doesn't know your name. Doesn't remember what you asked last week. That's the stateless LLM problem in a nutshell. The 5 systems we're covering today are the engineering answer to that problem. In October 2023, researchers at UC Berkeley published a paper called MemGPT, Memory GPT. The core insight was radical. Stop trying to give LLMs a bigger context window. Instead, treat the LLM like a CPU and manage memory the way an operating system does. It was the first serious attempt to bring oxygen monosulfide-level memory architecture to language models. MemGPT splits memory into 2 layers. The main context is everything currently loaded into the prompt: active messages, recent conversation, tool results. Think of it as RAM, fast but strictly limited by the context window. The external context is everything outside: a recall memory of past conversations searchable by meaning, and an archival memory for massive document stores. Think of those as the hard drive. Data pages in and out as needed. Here's the clever part. MemGPT lets the LLM control its own memory. When the agent needs something from external storage, it calls a retrieval function, exactly like an OS handles a page fault. While it's fetching, it runs internal reasoning loops, holding off the final response until it has what it needs. From the outside, it looks like the agent has unlimited context. From the inside, it's paging data in and out like a 1970s operating system. Elegant. MemGPT proved the concept. Letta turned it into production infrastructure. Letta is an open-source framework that grew directly out of the MemGPT research, and its goal is making agents truly persistent, not just within a session, indefinitely. In most agent frameworks, state disappears when the session ends. Letta writes everything to a database: conversation history, tool configs, memory state. Restart the server. Close the app. Come back 3 months later. The agent picks up exactly where it left off. It also ships with an Agent Development Environment, or ADE, that lets developers inspect and directly edit an agent's context window in real time. You can see and modify what the agent is currently thinking. Letta's key data structure is the memory block. Blocks are pinned permanently to the agent's active context, not retrieved on demand, always there. The human block stores everything about the user: name, preferences, behavioral patterns. The persona block stores the agent's own self-concept, its assigned role, its tone, what it said it liked last Tuesday. The agent edits these blocks itself using built-in memory tools, and developers can mark sensitive blocks as read-only, preventing the agent from accidentally corrupting critical information. In February 2025, LangChain released LangMem, a different angle on the problem. Where MemGPT and Letta focused on context management and persistence, LangMem focuses on extraction quality. The central question: how do you pull clean, structured facts out of messy, free-form conversations? LangMem's answer is something called Trustcall, a type-safe memory extraction mechanism. You define a schema up front using Pydantic, Python's data modeling library. User age is an integer. Interests are a list of strings. Dietary restrictions are an enum. When a new conversation comes in, LangMem's memory manager compares it against the existing schema and generates a structured update. No free-form text piling up. No contradictions accumulating in a vector store. Every piece of information slots into its predefined field, validated before it's written. And in multi-tenant systems, every memory item is namespaced to a user ID, so one user's data can never leak into another user's context. LangMem also tackles procedural memory, the how-to-behave knowledge that lives in system prompts. Instead of you manually rewriting those prompts when the agent makes mistakes, LangMem can do it automatically. The gradient optimizer breaks improvement into 2 explicit stages. First, critique what went wrong, then generate a specific fix. The meta prompt optimizer gives the agent extra thinking time to reflect on its own interaction history and propose better behavioral rules. Over time, the agent literally rewrites its own system prompt, a self-improving loop grounded in real interaction data. Now we hit a fundamental limitation of everything we've seen so far. Flat memory doesn't handle time. If a user moved from Tokyo to New York to London, a vector database ends up storing 3 contradictory facts about where they live, with no way to know which is current. This is where Zep and its graph engine Graphiti come in. Graphiti doesn't store text chunks. It stores a knowledge graph where facts have timestamps. Graphiti uses a bi-temporal model, 2 independent time axes on every fact in the graph. Validity time tracks when something was actually true in the real world. Transaction time tracks when the system first recorded it. When the agent learns the user moved to London, it doesn't delete the New York record. It sets the old edge's T_invalid date to today, marking it expired, and adds a new London edge with a current T_valid. The past survives. It's just marked as history. This makes it possible to reconstruct the exact state of knowledge at any point in time, critical for any system that needs to be auditable. Non-lossy. Nothing is ever deleted, only expired. And Graphiti's hybrid search combines semantic embeddings, BM25 keyword matching, and direct graph traversal simultaneously, keeping P95 latency under 300 milliseconds, even for complex relational queries. By mid-2025, the pattern was clear. Systems were getting smarter, but slower. Feeding the full conversation history into a prompt, the full context approach, hit 17 seconds of latency on the LOCOMO benchmark. 17 seconds. That's not a chatbot. That's a loading screen. Mem0 was built to fix this. Mem0 separates 2 things that every previous system coupled together: the write path and the read path. When a conversation happens, a background process extracts atomic facts, tiny, clean, self-contained pieces of information. The V3 algorithm makes this even leaner. Single pass, add-only extraction. No LLM calls to resolve conflicts during the write phase. That happens asynchronously, later. When the agent reads, it only sees a small, pre-processed fact store. The result? Responses in under 2 seconds, and a 90% reduction in token cost compared to full context approaches. For more complex reasoning, Mem0 ships a graph variant called Mem0G. It adds an entity extractor and a relations generator to the pipeline. Instead of flat text, it builds triplets. User prefers indoor venues. User dislikes crowded spaces. When new information conflicts with an existing triplet, the old relationship isn't deleted. It's invalidated, exactly like Graphiti. The result is multi-hop reasoning that flat vector search simply cannot replicate. And it achieves this while staying within a reasonable latency and cost budget.
So how do all these systems actually compare? The LOCOMO benchmark, long context memory, tests multi-session memory across 4 question types: single-hop fact retrieval, temporal ordering, multi-hop reasoning, and open domain questions.
Here's the 2026 leaderboard. Full context wins accuracy at 72.9%, but at 17 seconds and 26,000 tokens per query, it's not shippable. Mem0G scores 68.5% with 2.6 seconds and 4,000 tokens. Mem0 base hits 66.9%, only 6 points below full context, at 1.44 seconds and 2,000 tokens. That's a 91% latency cut and 90% token savings. LangMem drops to 58% accuracy, but returns only 130 tokens per query, ultra-lean for high-volume pipelines. OpenAI's built-in memory is the fastest at 0.9 seconds, but scores lowest at 52.9%, struggling on multi-hop queries.
The progression tells a coherent story. MemGPT taught agents to manage their own context like an operating system. Letta made that state permanent across sessions. LangMem made fact extraction type-safe and self-improving. Zep's Graphiti made time auditable. No fact is ever silently overwritten. And Mem0 made all of it fast enough to actually ship. Each system solved the specific failure mode the previous one left open. That's it for today. See you in the next one.